Hey everyone, and welcome. Have you ever looked at one of your gadgets and just wondered, how did this go from being just an idea to something that actually thinks? Well, today we're pulling back the curtain on that exact process. We're going to see how electronic systems get designed, from the very first blueprint to the final working brain. Let's get into it.
So really, how do all our everyday electronics get their smarts? I mean, think about it. From your coffee maker to an industrial robot, is every single one designed completely from scratch? The answer, most of the time, is a big no. Turns out, the secret for countless devices is starting with a kind of universal, reusable blueprint that you can tweak for pretty much any job.
And here it is. This is that starting point. What you're looking at is a block diagram for a general-purpose microcontroller board. Just think of it as the master plan for the system's brain. You can see all the main parts as simple blocks. You've got the MCU, the microcontroller unit, right there in the middle, and it's connected to an LCD display, a keypad, and some memory. It's the map that shows how everything's going to talk to each other before you even touch a single wire.
Okay, so we've seen the 30,000-foot view. Now, let's zoom all the way in and see how an engineer takes those simple blocks and turns them into a real functioning circuit.
You know, this first step is way more important than it looks. A block diagram isn't just some rough sketch, it's actually a super important tool for engineers. By mapping out all the parts and how information flows between them, they can figure out the system's exact input and output needs, what we call I/O. And that is what leads them to the biggest decision of all, picking the perfect microcontroller for the job.
This really breaks down the whole process for us. First, you use that block diagram to create your I/O budget. You ask, how many buttons, sensors, and displays do I need? Next, based on that, you pick an MCU that has enough pins and the right features to handle all of it. And then finally, once you've chosen the brain of the operation, you can take that simple block diagram and blow it up into a detailed circuit schematic, the real how-to wiring guide. And wow, here it is. That's quite a difference, right? We went from a few neat little blocks to this incredibly complex web of connections, components, and part numbers. This is the schematic for our base system. Every single line you see here represents a physical connection that has to be made for that display, keypad, and memory to actually work with the PIC16F877 microcontroller that's running the whole show.
Of course, building the hardware is only half the battle. How do you know if you actually wired everything up correctly? Well, you need a test program. And I love this quote from the source code because it's so direct. Its only job is to exercise every single part of the module. It's got to check the analog input, write something to the LCD, read the keypad, and talk to the memory. It's basically the final quality check to make sure the hardware is good to go. All right, so our base system is built, it's tested, and it works. But what if your project needs a little more horsepower? Well, the great thing about this Bluepoint approach is that you're not stuck. You can expand it. It's kind of like adding more RAM to your computer. You can give your system a bigger brain by adding more memory.
Now, our original system used something called serial memory. It's great because it uses very few of the microcontroller's I/O pins, which is efficient, but it's also kind of slow. So if your project needs more speed, you can upgrade to parallel memory. And as you can see, there's a really clear trade-off. You get way faster data transfer, but it's going to cost you a lot more I/O pins to hook up those memory chips.
And here's what that upgrade looks like on paper. We've added two big 32K RAM chips. Now, to manage them, we're using almost all of the microcontroller's port C and port D just for data and addresses. So by sacrificing all those I/O pins, we've given our system a massive boost in its short-term memory and its overall speed.
Okay, we've seen the blueprint, we've seen how to upgrade it. Theory is great, but now let's see how all these ideas come together to solve a real-world design problem.
So here's the mission. Design a super reliable controller for a commercial refrigeration unit. You know, like the kind you'd find in a huge temperature-controlled shipping container. It's got to keep a precise temperature, have a display, let the user change settings, and, most importantly, sound an alarm if anything goes wrong. This is a perfect real-world test for our whole design process. And where do we start? You guessed it, with a block diagram. This is the blueprint for our refrigeration controller. Over on the left, you've got the inputs, 4 temperature sensors for redundancy, and some ups-down buttons to set the temperature. And on the right, the outputs, the display, a couple of alarms, and the big one, the relay that turns the cooling compressor on and off.
So from that block diagram, we can create our I/O budget. It's just like accounting. We need 4 analog inputs for those sensors and 2 digital inputs for the buttons.
For outputs, we need a bunch of digital pins to run that 7-segment display, one for the compressor relay, and at least 2 more for the alarms. Once you tally all that up, the engineer knows exactly what to look for in a microcontroller.
Now, that refrigeration unit is just one example. The core skills, making a blueprint and budgeting your I/O, can be used for pretty much any electronic project you can dream up.
So how do you actually choose one? Well, manufacturers offer a massive range of microcontrollers, from tiny little 6-pin chips to absolute 80-pin beasts. Your choice really just comes down to matching the chip's features to what your project needs. Do you have enough I/O pins? Enough memory? Does it have the right built-in tools, like an analog-to-digital converter or timers? Your block diagram and I/O budget will give you all those answers.
So there you have it. We've gone all the way from a simple block diagram to a detailed schematic. We've expanded its capabilities, and we've even applied it to a real-world problem. You now have the fundamental blueprint for how smart devices are designed. So the only real question left is, what are you going to build?